I'm Hannah Nameniuk, and I'm going to walk you through the action potential. So first I have this beautiful graph of the change in the membrane potential over time due to an action potential. So as you can see here, the part labeled A is depolarization, which is an increase in membrane potential from negative 70 up to about plus 35 millivolts. And then the part labeled B is bringing the membrane back down to that resting potential of negative 70 millivolts. And part B is repolarization. And then part C is hyperpolarization before returning back to the resting membrane potential before another action potential can occur. So down here, A, depolarization. So this is a portion of the membrane of a neuron, and I have 3 different channels shown here, and the ion gradients drawn in. So before depolarization occurs, there are more sodium ions on the outside as compared to the inside, and there are more potassium ions on the inside than the outside of the membrane. And then this channel here is a leak channel, a potassium leak channel, which remains open, and then at all times that remains open. And then this purple one here in the middle, that is our sodium voltage gated channel, and then this is our potassium voltage gated channel. So in depolarization, the leak channel is always open for potassium, and then the sodium channel is open by a change in membrane voltage, causing the sodium to move into the cell through this channel, which is the reason that the membrane potential increases as in the graph there. And then in part B, repolarization. So this is when the membrane potential begins to return to normal, and this occurs because the voltage-gated sodium channel is now inactivated, meaning no sodium can go in or out of the membrane. Again, the potassium leak channel is always open, but now in repolarization, the voltage-gated potassium channel is open, which allows potassium to leave the cell, causing that repolarization seen in the graph there. Then, in hyperpolarization, again, we have the always open potassium leak channel. Now, this is drawn a little bit differently than above. So above in part B, the sodium voltage-gated channel is inactivated, where in hyperpolarization part C, it is closed, not inactive. So in part B, inactive means that another action potential cannot occur at that time, where at this time another action potential could occur since the channel is only closed and not inactive. But being that it is closed, sodium is neither entering nor leaving the cell at this time. And the reason hyperpolarization is occurring, which is going past the resting membrane voltage, so more negative than negative 70 as seen right there, is because some of these voltage-gated potassium channels stay open, allowing more potassium to leave the cell. And that is what causes that repolarization, or that hyperpolarization after repolarization.